Welcome to the session on forces in motion, pulleys. The objectives for this session are to solve problems involving connected particles and pulley systems. We will explore how to model systems of connected particles which involve pulleys. The assumption that we will be making is that particles are connected by a light, inextensible string passing over a smooth pulley. The practical implications of this assumption are that the tension in the string is the same on both sides of the pulley. Also, the string is horizontal or vertical on each side of the pulley. Note that as particles are moving in different directions, a system involving a pulley cannot be treated as a single particle. So let's now take a look at an example. A light, inextensible string passes over a smooth, fixed pulley. The particles P and Q of mass 5m and 6m are attached to the two ends of the string, and the masses hang with the string taut. So let's take a look at what's going on. Here's our pulley. We have the light, inextensible string passing over it. We also have particles P and Q of mass 5m and 6m, as shown, attached to the two ends of the string. The weight on particle P is 5 mg newtons, and the weight on particle Q is 6 mg newtons. We also have that the masses hang with the string taut, so we have the tension as shown. The acceleration will be moving in the direction indicated. Pause the video and have a go at this example. Press play when you're ready to view the solutions. Let's have a go at example 1a first. We are required to write an equation of motion for P and an equation of motion for Q, and hence find the acceleration of each mass. So let's solve this. Since F equals ma, we have for P the force in the direction of acceleration is T minus 5 mg equals the mass, which is 5m, times a, which is the acceleration. For Q, similarly, in the direction of acceleration, we have the force, or the net force, which is 6 mg minus T, equals the mass, which is 6m, times the acceleration, a. We're now going to solve for a and for t. We have two equations in two unknowns. Adding the equations gives us mg equals 11 ma. And therefore, a equals g over 11. And now for part B. We are required to find the tension in the string and hence find the force exerted on the pulley by the string. So let's solve this. From one part A, we have that A equals g over 11. And we also have these two equations. We can substitute A into any one of these two equations in order to find T. We're going to select this one. Substituting A equals g over 11 in this equation gives us T minus 5 mg equals 5m g over 11. and rearranging gives us T equals 5 and 5/11 mg. So the tension in the string is T equals 5 and 5/11 mg. From the diagram, F equals 2T, and therefore substituting T into this equation gives us that F equals 10 and 10/11 mg. And now for part C, we are required to find the distance moved by Q in the first 3 seconds. So let's solve this. We know that U equals 0, A equals G/11, and T equals 3, and we need to find S. Which equation of motion are we going to use? We are of course going to use this one, S equals UT plus a half AT squared, as this has all the letters indicated in it. So plugging in the values, of course we're looking for S, so S stays as it is. This is the distance. U equals 0, A equals G/11, and T equals 3. And then solving gives us S equals 9G/22. And now for part D, we are required to state how we have used the assumption that the pulley is smooth in our calculations. So let's solve this. For this, we are simply required to state or observe that at P and Q, the tension in the string is the same. This brings us to the end of this session. If you have understood its contents, you should be able to solve problems involving connected particles and pulley systems. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.